Thank you for inviting me here. So as you see from the title, we are going to talk about evolving robots. So robots that are not programmed by a designer, by a researcher, but that develop the ability through an automatic process that is analogous to natural evolution. Before entering into that, let me introduce a little bit some notion about robots, in particular about autonomous robots. The term autonomous refers to robots that operate without human intervention, so not teleoperated robots, for example, which are completely different from that in that respect. Now, what is a robot? A robot is a machine that has several components. One is the body. This is one of the is a vacuum cleaning robot, one of the few robots that has been commercialized in large numbers. So in this case, the body is this plastic cylindrical object. The second important component are the sensors. In this robot, there are electronic sensors placed around the body that, for example, are used to detect the presence of obstacles near the robot, and other type of sensor. Then we have motors that enable this robot to move. This is a robot that cleans autonomously an indoor area. Okay, so the actuator in this case are motors enabling the robot to move by moving the wheels. And finally, there is a sort of brain of the robot, which is typically it's realized as a software running on a computer, which is on the robot, on board the robot. This computer and this software is interface connected with the sensor and with the motors of the robot. So the role of the brain is that to, on the basis of the state of the sensor, decide how to move the robot, for example, in order to achieve a given function. In this case, cleaning a room, for example. This is instead a humanoid robot, so a robot with a completely different morphology. The body, in this case, has a human-like skeleton. It's made of a piece of metal, plastic. Again, we have sensors, several types of sensors in this case, cameras mounted on the eyes, microphone on the ears, tactile sensor on the fingers, on the hand, and so on. We have motors. In this case, motors are electric motors that control the joints and so enable the robot to move the arms, the fingers, the torso, etc. And again, we have a brain, which also in this case is realized as a software running on a computer. The computer in this case is placed on the head of the robot, but it's not particularly important from that point of view. It might be placed in other parts or even outside the robot. The important aspect is that the brain gathers information from the sensors and control the motors, determine the motion of the motors. So there are robots with completely different morphology. This is, for example, is a quadruped robot produced by the Boston Dynamics company, which is a robot with quadrupedal shapes that is able, in particular, to work on irregular terrains, as you see from this picture. Most of the robots that we have today are made of rigid materials, but now there is also a new type of robot coming, which are more interesting, which are made of soft material, like, for example, this fish robot or this octopus-like robot. Okay, so this is a robot that can perform, can manipulate object, can grasp an object, but in a completely different way from a humanoid robot, of course, by using the sort of tentacles, which is actuated through motors, etc., etc. Now, so from this example, you can, you can have an idea of the fact that the technological level is already very advanced. We can construct robots that are quite complicated, quite differentiated. They can play potentially different functions. However, the level of intelligence of this robot is still rather limited with respect to animals and humans' level of intelligence. Okay? So this is the reason why there are only few robots that are really commercialized and used in big numbers. And most of the robots are still prototype that are used in research lab, but are not yet robust enough to be used in the real world. Now, we might of course, hypothesize why this is so. So what is the problem? Why we are not yet able to realize more intelligent robots? There are, of course, different possibilities. In general terms, we can hypothesize that one possible reason is that there is some missing ingredients. So there is something that we didn't understand yet that is missing from this system. And so if we manage to add this additional ingredient, then the level of intelligence of the robot that we are able to build will increase. For example, in a presentation yesterday, Professor Garziano was claiming that having consciousness, so being conscious, having a robot or machine that are conscious, it's a critical factor for producing more intelligent machine, more intelligent robots. Okay. There is another possibility, however, which is the one in which I will insist more in this presentation, which is that one problem might be that the design technique that we currently have are inadequate for developing robots. That might be surprising because, of course, we humans have been able to construct, to develop very complex artifacts, such as airplanes or computers and things like that. But the point is that robots are intrinsically different from other kind of systems. And so this difference might imply that the technique that are effective for designing certain artifacts are not necessarily effective for designing robots. So now, why robots are different? There are a set of reasons that make them different from other machines. One important aspect to consider is that robot has to produce behaviors. Okay, so they are not just systems that receive an input information, elaborate the information, then take a decision, as many computer programs, for example. What a robot should do is to, on the basis of the perceptual state, start to make action, start to move, and then, as a result of this movement, the information that the robot perceives change, because as in the case of a human, what I see depends on my position in the environment. And if I move, if I turn my head, what I perceive change completely. Okay? So they have to produce a sort of process, dynamical process, which is a sequence of micro action that at the end produce a behavior which is something such as gathering food or collecting an object or doing some function. Okay. So behavioral systems are intrinsically different from other kind of systems that, for example, take decisions on the basis of huge databases. There are also other reasons. The other important reason is that the robot has to operate on information which is sub-symbolic. What do you mean sub-symbolic? Computers typically operate with symbols, words, sentences, documents, which are made of conventionalized things, words of our language. Okay. While a robot has to operate on the basis of physical quantities. They perceive light, they perceive sounds, which are continuous elements. And this information has to be interpreted. And this information has several characteristics which make the things hard. So it's noisy, there is a lot of noise, it's often incomplete. I can perceive only part of the object because part of the object are behind, and so they cannot be perceived directly. Also, the information that a robot perceives is limited. That doesn't have access to a full description of the environment around him, but only a partial description, and so on. So all these differences imply that a robot is something intrinsically different from other kind of artifact of the machine. And as I will try to stress also in the rest of the presentation, this has implication on the design. Because basically, since there is an indirect relationship between, let me say in other words, so it is important to understand that the behavior of a robot, as I will try to show with example, is not just a manifestation of the brain of the robot. Okay? Is instead the result of a continuous interaction between the robot body, the environment, which is orchestrated in some way by the brain, but is not a direct product of the brain. Okay? So understanding this relationship is complex, and understanding how the interaction should be regulated in order to produce a certain desired behavior is complicated, it's difficult from the point of view of a human designer. Now, evolution and also evolutionary robotics, as we will see, in a sense, is not affected by this design problem. Because evolution is a sort, as Dawkins said, is a blind watchmaker, which means that design things without understanding why certain aspects of these things are functional or produce a desired outcome. Okay? The way in which evolution operates at a high level of abstraction is that by producing variation, through exploding genetic variation, and selecting the variation then produce an improvement that produce an increase in performance, for example. So to realize this process, which is a sort of trial and error process, evolution does not have to understand why a specific characteristic, why a specific variation is capable in interaction with the environment to produce a desired outcome, a desired behavior. The other aspect, because this methodology is interesting, is that it's sort of enabled to develop solutions that are hard to imagine from a human point of view. So basically, we do not have to specify how the robot should behave, how it should move in order to achieve a certain function. This will be automatically the result of the evolutionary process. Now let me explain a little bit more the methodology, which it's relatively simple. So as in the case of natural evolution, we work on a population. So we have a population of robots that change through generations and that possibly evolve, get better. For each robot, we have a genotype, an artificial genotype, which basically is a sequence of numbers, typically. Okay? So like in the case of a real genotype, is a sequential information that specifies the characteristic of the corresponding individual, the corresponding robot in this case. So we have a population of this genotype, which is initially in this experiment is just generated randomly. Okay, so we have population of initial random robot. Then each of these genotype is transformed into a corresponding robot that is placed in an environment and evaluated for the basis of performing a certain function. The function that the robot should perform is the only aspect that the designer specifies. So I might want to have a robot which is able to clean my house, or I might want to have a robot which is able to walk as fast as possible. So I, as a designer, specify the function, and then I use this function to evaluate this robot, to evaluate how good it is at performing that function. Okay. This is repeated for all the robots of the initial generation, which of course, given that are based on random genotype, will not perform very well. We have very limited performance, very low performance. Despite that, some of these genotypes will be better than others, and so will be selected and used to create a new population of genotype. So that basically means that the individuals which are better have the possibility, are selected, and have the possibility to create other individuals similar to them, which, however, also receive variation, sort of mutation that change the number in the genotype sequence, and so change the characteristic of the robot. by repeating this process many times for many generations, we might obtain better and better robots. This is a technique which is called evolutionary computation in general. It's a technique which is not only applied to robots, it's also applied for evolving software or for solving other type of problems, which can, however, be applied to evolve robots. Okay, so that's what I wanted to say in the introduction. And I will now try to illustrate this aspect with examples. In particular, I will discuss three types of examples. The first one are experiments involving robots in which also the morphological characteristics, so the shape of the robot, is encoded into the genotype, and so it's subjected to evolution. So that means that the robot change their body shape throughout generation, and they evolve possibly a morphological structure which is effective for performing a certain function. Then I will show other type of experiment that look to the development of behavioral and also form of cognitive capabilities, such as, for example, the ability to understand language and to communicate. And finally, I will show some example of what is called swarm robotics. So basically the usage of many robots, not just a single robot, many robots that coordinate and cooperate to perform a certain function. So now, to understand why the morphological characteristics are important, we should it's important to say that obviously the morphology is critical. So, for example, a robot that can fly might have a certain type of morphology. Typically, it will be light, not too heavy, which is suitable for flying. And of course, a robot that should walk might have a different morphology. That's obvious in a sense. So depending on the function that we want to achieve, the morphology will be different. But what is less obvious is that even the fine-grained characteristic of the body influence in an important manner the capability of the robot. To explain try to clarify this aspect, we'll use this example of a passive walker machine. Now, as you can see from this video, a passive walker machine is a machine which is able to walk, in this case on a slightly inclined plane, so on a slope. And what is remarkable in this machine is that they do not have any sensor, any motors, any brain. So they are just pieces of metals connected together. They are connected through passive joints, so they are connected to joints that are not actuated by motors. Okay. Despite of that, as you saw, they might be able to walk. So that's in a sense is a little bit surprising. But indeed, this is strongly related to the way in which we humans work. So basically, our ability to walk is primarily the result of our body structure, and only secondarily is the result of our nervous system orchestration role. Okay? So also our way to work is exploit this passive process, which basically means that we can construct a machine that works, but that basically do not use motor because it exploits the gravity force and the effect that the gravity force and the collision of the feet with the ground produce, so that the different parts of the machine start moving and produce a periodic swinging of the two legs, and yeah, we have the working behavior. Okay, so basically, one behavioral capability can be produced entirely or to a good extent just by the characteristic of the body, without using any brain, without using any sensor. However, there is a caveat to consider. If we change slightly the characteristic of this machine, so for example, if we make this segment slightly longer, or if we make the different part a little bit heavier or soft or less heavy, the machine might stop working. Okay, so that's imply that the characteristic of the body should be tightly tuned so to produce the working behavior. Okay, and it's rather difficult from a designer to understand why a certain specific configuration of length and elasticity maybe can produce a working behavior, and so how this kind of machine can be designed. Now let's see how artificial evolution can produce robots or creatures with varying morphology and manage to discover the right combination of physical parameters that enable to produce desired behavior. We show you this with this example, in which these are sort of strange creatures that are made of cubic cells. So there are 4 types of cells that are used in this experiment. Sorry, let me go back. So the red cell and the green cell are muscle cells. So basically, they are cubic objects that contract and then expand, or expand and then contract. Okay. Then we have not moving cells of 2 types. We have bone, which are rigid cells, and we have tissue, which are soft cells. So they do not move by themselves, but they are soft and so are elastic. And we can construct a creature, we'd say, composed by many of these cells, like the one that you saw here on the top part of the slide. Now, if we choose the right combination, we can produce creatures that can walk. And how we can do that? I mean, guessing how they have to be placed in order to produce a working behavior is rather difficult. But what we can do is that we can encode in our artificial genotype a number for each of the possible cells, specifying whether the cell is of type 1, 2, 3, or 4. We create a population of this genotype, and then each genotype generates a creature. The creature is placed on an environment, which in this case is just a surface, and is evaluated for how good it is in moving, how fast it is able to move in a given amount of time. And so those are the results that you get, which are quite strange, but they are capable of performing the function. And so this is give you a little bit an idea of the process. So when you start at the beginning with random genotype, you have creatures that have very low performance and that have a morphology which is not particularly structured or elaborated. Then generation by generation, as a result of random change and a result of the selection process, you get a progressive modification of the morphology of the creature and an improvement in performance. This is the fitness, so is the criteria that measure how good is the robot, which in this case is just measuring how much is able to travel within a given amount of time. This is an example of a simulated system, but other experiments have been used to evolve robots that have been realized in physical systems. So this is another experiment, for example, in which the robots are made, in this case, by segments of different legs combined in different ways. The relationship between the genotype and phenotype, so the relationship between what is written in the genotype and how this is translated into the phenotypical robots, is a little more complicated in this case. Again, this is a machine have been evolved for walking, and those are examples of solutions found by the evolutionary process. So the evolution is often performed in simulation, but then the simulated robot might be manufactured, in this case by using a 3D printer. So the description of the phenotype is translated into a physical object, and which also has models put inside that generate the movement and produce the working behavior. Last example that I want to show you regarding this type of experiment is this other video that show swimming robots. So again, we have a system in which the genotype specify the morphology, and in this case also there are specify the characteristic of neurons that control the movement of the joints between these parts. And these are result of different runs, different evolutionary runs. So you see that this should give you an idea of the creativity of the process. So how this process of selection and variation can produce different kind of solution that will be hard to imagine or to design by a human. Okay, let me move to second set of experiment. Now we'll abandon the idea of evolving the morphology of the robot. So we will use robot with a well-defined fixed morphology, in this case a humanoid robot that I was mentioning before. And we will concentrate only on the evolution of the brain. I didn't say much up to now about this aspect, but in this experiment, basically, the brain is realized as an artificial neural network. Okay, so it's an object that it's made of neurons, so unit that has a certain level of activation and that are connected through connection, which have different strength, so that determine how a neuron, whether a neuron activate or inhibit other neurons. So they are a sort of model of real, simplified models of biological neurons. Okay. These networks are composed by different types of neurons. We have sensory neurons, shown in this case on the bottom line, that encode information extracted from the robot sensor. So there are, in this case, for example, there are robots that encode the information detected by the camera, by the sensor that encode the position of the joints, of the arm and the finger. And also, in this case, this robot hear sentences. So the user might talk to them, ask them to do some behavior. And so they get this linguistic information, as an input here in this other sensor. Then we have internal neurons, and then we have motor neurons that control, that determine the force applied to the motors, which control the joints of the robot. Okay. So this is a particular way of realizing the brain of the robot, which of course take inspiration from real brains. You can realize brain by using a different language, so to say, or a different style. But this technique works especially well for many reasons, but I will not go into details for reason of time. Okay, so in this case, what we have is that the genotype of our evolving robot encode the characteristic of the brain. In particular, encode the strength of the connection among neurons. So encode, for example, whether these neurons has a positive or negative connection and how strong this positive or negative connection is. These determine how the robot responds to the sensory state that he perceives. And so at the end, it contributes to determining the behavior of the robot. What we did in this experiment, as I was saying, is to evolve robot for the ability to understand simple sentences, such as, for example, grasp the blue ball or move the blue ball, by producing the corresponding behavior. So these are examples of evolved robots. This is the sentence that is produced that a robot hears and that trigger the corresponding behavior in the robot. Okay. Now, let me say a little bit about why we did this experiment. The idea here was to study how a robot can develop an ability to comprehend language, and to understand the meaning of words in a deep sense, so to say. So this robot basically has to develop several integrated capabilities. On one side, they have to understand that the meaning of the sentence. So to understand that, for example, the sentence refers to a specific object, and that, the action that should be produced is a certain type of action. Okay? But the robot should also be able to, as a result of evolution, is also able to develop behavioral capabilities, such as grasping objects, moving objects, manipulating objects in some way. And finally, it should be able to connect the meaning of the sentences with the perceptual state and with the action that has to be performed. There are systems that you might be familiar that are able to comprehend natural language, such as, for example, in applications such as Siri or Google 9 on mobile phone. Okay, so in that case, you can talk to the phone and ask the phone to do something, and the phone will respond, for example, by triggering a navigation map. Okay. One aspect, however, is how deep is the comprehension that the machine has of the natural language. Okay. If you want to have a system that, I mean, at the moment, this system have a very superficial comprehension. If you want to have a deep comprehension of similar to the one that we have, you have to be able to connect this information with sub-symbol information coming from sensor and through behavioral capabilities. Let me make an example. For us, if you think of the word chair, for example, or seat, of course, it is associated with a certain shape. So we know that certain type of object might be used as chairs. We know that chairs might be used for sitting. However, to fully understand what a chair is, we have to be able to sit on the chair. Because if we sit on the chair, if we are able to produce this behavior, we feel that we can relax our muscle and still remain suspended over the terrain. Okay? So if we have the behavioral part, we manage to associate the meaning to information that it's impossible to gather if we are not placed in the world, if we're not able to operate in the world. So basically, in this way, we can try to construct machines that have a deep comprehension of words. And for example, these robots are still limited in terms of complexity of vocabulary. They can understand only few different words and few types of sentences. But for one interesting aspect that they have is that they understand the compositional nature of language. So for example, if you evolve the robot for the ability to understand certain sentences, but then you ask the robot to you ask the robot with a new sentence to reproduce a new behavior, it tends to understand and generalize its capabilities. So he understood that the meaning behind the sentence has a compositional nature and is connected to the world in a specific way, so that you can understand new combination of words. Of course, I'm going very fast. I hope to be not too fast. This is an experiment which is still even more ambitious in a sense. So imagine that, that you want to see whether a group of robots that are evolved for performing a certain function manage to discover a communication system and use it to coordinate. Okay. So that's what we try to study with this research and this experiment. What we did was, in this case, we used more simpler robot, with a robot with different type of sensors, infrared sensor, ground sensor, microphone. These robots can perceive obstacles around them, can detect the other robot, the position of the other robot, can move through the wheels, and can also produce sounds and hear sounds. The sounds are just the sound of different frequencies that can be produced by the robot. Okay. And then we we created a situation which is shown here, in which basically we imagine that there is a sort of nest and foraging area, and so that the robot has to find this area and then to move to bring the food toward the nest. Okay, so they have to move back and forth between the two areas, but they cannot perceive the area by distance, and therefore they can only perceive the color of the ground in which they are located. So they might use communication to inform the other robot about where they are located, and so where for example, the nest is located. The methodology, the process is always the same. So we are using a population of artificial genotype that encode the characteristic of the brain of the robot. How the neurons are interconnected, the strength of the connection. And we change, what we define is the fitness function. So the criterion that is used to evaluate how good these robots are. In this case, they are just rewarded every time they manage to bring food from the foraging area to the nest. Okay. We do not tell to the robot that they have to produce sound. We will not tell to the robot which sound they have to produce, how they react to sound, how they should move in the environment. This is something that they have to discover by themselves. And indeed, they do. And so I will show you just an example. First in simulation and then on the physical robots. So you see, those are evolved robots. They start to move in the environment, explore the environment. They find the two areas and then coordinate. They coordinate by also using signals. I will try to give you an idea of the type of signal they produce with this second video. Sorry, for some reason the sound doesn't come out from the computer. Anyway, so okay, so they use also the possibility to produce sound. And what they do is that they produce sound with well-differentiated frequency in different parts of the environment. In particular, they produce a sound with a low frequency when they are located on the black area, and a sound with different frequency where they are located outside. Notice how the way in which they coordinate. So there is one robot waiting on the black area, oriented toward the other robot in the white area, and then the robot from the white area exit and enter on the black area, and the other robot is already oriented in the right direction, then move toward the white area. Okay. Now, something that we can do with this experiment is also to look at how these abilities are developed through generations, as we saw in the previous example. And so we can study how this ability to coordinate to solve this problem progress throughout generations. And basically, what we see is that the robots of the first generation have very simple behavioral capabilities, such as they start to avoid obstacles and to move randomly in the environment by exploring the environment. But then, generation after generation, they develop new capabilities that are added on top of the base on the previous developed capabilities. And at the end, all these behavioral and communication capability enable them to produce the behavior that you saw. One interesting aspect, the only things that I want to mention about this, is that by analyzing this process, again, we can see how there is a strict interconnection between how they behave and what they manage to communicate. For example, an interesting aspect is that this robot cannot perceive whether the center of this area. They can only know that they are located on the area. Despite of that, they manage to communicate where the center of the area is located. And this is done by producing the behavior that I was describing before. So they move along the border and then assume a relative position with respect to each other, so that the robot exiting from one area knows that by traveling on the right, that the other robot will enter into the center of the target area. Okay. Now, this aspect is interesting because it means that by acting in this way, by discovering this behavior of moving along the border and waiting to see the other robot, they manage to generate information, to construct information, which is then communicated by the sound. Okay? So basically, this shows how the meaning of the signals in this robot is constructed through behavioral process, through motion processes. So the meaning is not just a picture, a description of something. Is something that can be generated by acting in the world. And this is what this robot discovered. Last topic, I think I should speed up a little bit, is evolving, or in any case, using groups or large groups of robots. Okay. This is a hot topic in robotics because collective system can have many advantages. For example, as you see in this picture here, they might enable robots to cooperate and to solve problems that they cannot solve alone. For example, they might pass through a gap which will be too hard for a single robot by self-assembling together. This is something, for example, that ants typically do. To cross like a small river, they mount on top of the others, so to construct a physical structure that enables them to overcome the water barrier. Okay. So there is research going on trying to build robots inspired by this characteristic of social animals, in particular social insect, bees, but also fish, etc., that typically manage to display effective capability by using many individuals, which are simple, but that by working together in the appropriate manner can perform complex behavior, complex tasks. This is an example of a nest built by termite that, as you can see, is a huge structure with a complicated architecture, much larger than the size of a single termite. Okay. So there is research going on trying to build robots that can do something similar, heavily inspired by behavioral social animals. I will show you this example. This is a project to which I participated together with colleagues from Switzerland and Belgium, in which you see an example of many robots of different types coordinating and cooperating to perform a certain function. So you know that in social insect, often the population is divided in castes or groups, such as, for example, working and soldier ants, which have different morphological structure and are specialized for performing different functions. So in this case, in the case of the project, we try to construct something similar. So we have robots with different morphology. Some are specialized for moving on the terrain. So they move through wheels, as you see here. Some other, like this robot here, have small arms that they can use to manipulate objects, or they can use to climb over surface. Other are flying robots. And they are complementary in the sense that, for example, flying robots are used to explore the environment, and due to the possibility to have a long vision range by observing the environment from the top. And so they are in particular used in this example to find the target object that has to be collected. While the wheeler robot and the manipulator robot are used to coordinate in order to perform a function, in this case, retrieving a book and bringing this book to the user. Okay. This is I should go fast because I want to leave some time for questions. This is another example in which you see the idea of self-assembling. So those are robots that are able to attach one another, so to be able to, for example, move in very irregular terrain by exploiting the interaction between them. So you see each one is an independent robot, acting on the basis of its own sensory state, but they are designed in a way, again, by using evolution, so to be capable of operating as a team, or as a cooperative team. And one important aspect in robotics is generalization that was mentioned at the beginning. It's extremely important because this is another difficulty of robotics. A robot will always experience different kind of condition. If you place a robot here today and tomorrow, the light condition will be different. The position of the object will be different. So if you build a robot that it's able to work well in a very specific environment, it's useless, because basically robot has to be able to generalize. Robot has to be able to deal with variation in the environment. So one important aspect that the robot should have is this generalization capability. And one interesting characteristic of the robot constructed to this methodology is that they are particularly robust, and they often display generalization capability. Why they are robust? But basically because of the trial and error process, the fact that they have been evolved and tested and evaluated in many different conditions throughout evolution, ensure that only robust solution, only robust robot are evolved, are retained, are selected. The ones that are not robust are discarded within the evolutionary process. But we can do even something more. You saw the robots before that are evolved just for the ability to moving together in an environment without obstacles. Now, if you place the same robot in an environment with obstacles, you can observe that they continue to coordinate, but they also show new type of behavior that were not possible, that were not shown in the other environment. So, for example, they automatically show an ability to collectively avoid obstacles, or to rearrange their shape, the way in which they are interconnected as a result of collision, so to negotiate narrow passages. Okay? So in this case, in this example, they have to reach a target, and they do so by alternating this sort of moving obstacle avoidance behavior. And when they start to perceive the target, they tend to move in the direction of the target, and as we will see, they manage to do that by squeezing over these narrow passages. All of this is realized by using an extremely simple nervous system that just operate on the basis of distraction information. That is, they feel how much they are pulled by the other robot, or they are pulled by the collision with the obstacles, and sensors that provide information about the target. So another interesting aspect of using this methodology is that the solutions that tend to be evolved are typically very compact at the level of the control rules, at the level of the brain. Despite of that, so they are so nicely tuned together, nicely co-adapted together, all the components, that enable them to produce interesting behavior. In a sense, it's similar to what you might observe exactly in social insects. Social insects are relatively simple at the level of the sensory and behavioral capability that it has at the individual level, but taken together can perform very complicated functions. Okay, so let me conclude basically with the main messages that I wanted to carry with the presentation. The first things that I try to emphasize is that robots are systems which are fundamentally different from other type of artifacts. Okay? So they are systems that has to be able to produce behaviors which are dynamical processes. These processes are not just a manifestation of a brain that decides what to do. They are a manifestation of mostly the interaction between all the components of the robot, including the body parts of the robot and the environment, regulated, orchestrated by the brain. Okay? For this reason, these systems are hard to design. It's hard to design from an observer how a robot should be made, should be constructed, so to produce an interesting behavior. This is a problem for design technique, but can be an opportunity for learning techniques such as evolutionary robotics, because these techniques, as I stressed, do not need to understand the complex relation between this fine-grained characteristic of the brain, the fine-grained characteristic of the body, and the behavior that came out. They just operate by capitalizing on variations that are useful. And also, something that I try to convey is the fact that the solution that you can obtain by using this methodology are qualitatively different from the robot that you can obtain by programming them, by designing them. And they tend to resemble much more at a certain level of description to natural organisms, to real animals, to the way in which natural systems operate in the environment. So I thank you. Stop here, and if there is any question, we'll be very welcome.